Welcome everybody to the last video lecture in week 3. This week we have looked at various proof techniques and we will continue to look at more proof techniques in this particular video lecture. So till now we have seen that we have talked about that to prove A implies B, there can be many proof techniques. Namely constructive proof, proof by contradiction, proof by contra-positive, induction, counterexample and existential proofs. Till now we have seen constructive proofs, proof by contradiction and proof by contra-positive. Now here I again repeat this thing that I repeat in every of these video lectures, namely which proof to apply for which problem is something that you have to decide for yourselves. Some of the problems can be split into smaller problems that can be easier to tackle, while some of them can be viewed in a different way, and by viewing so one can make the problem easier. But which problem to split and how to split it or how to look at it is an art in itself that you have to develop. In this particular set of video lectures, we will be giving you thumb rules on which one to use, which proof technique to use for which problem. But at the end of the day, you will have to make a choice for yourself. Many of the problems can have multiple different proof techniques that is good enough for it. We also looked at some of the simple techniques of how to split the problem into smaller cases. In particularly, we looked at this following two techniques. First of all, if B can be written as C and D, then proving A implies B is same as proving A implies C and A implies D. And in this case, one can split the problem of proving A implies B into these two parts, A implies C and A implies D. There is also the other thing of removing the redundant assumptions. In other words, sometimes some assumptions are there which are not necessary. So in other words, say if I have been asked to prove A and C implies B, one might throw away the C and end up proving A implies B, which is good enough for us. So in other words, what I am saying is that one should extract the most relevant set of assumptions that are necessary to prove B. That would simplify the proof, or rather they will simplify the problems and help in getting the proof easier. The third part was that sometimes proving something stronger is easier. So while we might have something like C implies B and we have to prove A implies B, it might be easier to prove A implies C instead, which would be a harder problem in itself, but might be easier to prove. So in that case, making the problem harder can make our life of getting a proof easier. Other than these three tricks, we also saw some proof techniques. In particularly, we looked at constructive proofs, and in that we saw direct proofs. So in direct proof, the idea is that to prove A implies B, we start with the assumption A and step by step go on to prove B. But sometimes by doing so or doing such a thing, the proof can become very magical, and hence one can imagine that it is hard to get such a proof. Another technique that can be there is what is known as a backward proof. So in this technique, to prove A implies B, the idea is to simplify B slowly till the time you simplify it to a different form So namely, if I can simplify B to C, then A implies B would basically mean A implies C. And since A implies C is a simpler statement, it will be easier to get that proof. So this was the constructive proof, and in which case we saw the direct proof technique. There was the other proof technique in the constructive proof, which is called the case studies. The idea is that sometimes the assumptions of the premise can be split into different cases, and in that case we can split the problem according to cases. Namely, if A can be written as C or D, then A implies B is same as proving C implies B and D implies B. Here it is important to note that how to split A into these two things, C or D, is something that requires some amount of art and understanding of the problem. One would like to split up into C or D in such a way that proving C implies B and D implies D becomes easier. We have of course seen examples in all the various problem case studies that we have seen, or various proof techniques that we have seen till now. Now the third one that we saw, the proof technique, was the proof by contradiction. The idea was that to prove A implies B, one can also end up proving not B and A is false. So this is called the proof by contradiction. So there we assume that B is not true, and we work our way through till we get some weird statement which is always false. A very similar statement to this same technique is what is known as the proof by contra-positiveness. There, the idea is that proving A implies B is same as proving not B implies not A. And sometimes proving not B implies not A can be easier to prove. So in particular, if B can be written in the form of C or D, in that case A implies B, which is same as not B implies not A, is same as not B, not C and not D implies not A. So this form of not C and not D implies not A is sometimes easier to prove. One thing to note is that all of these things are similar. All the proof techniques are similar in the sense that they all are different ways of writing A implies B. So all problems can be solved with any of these proof techniques. But it so happens that some of the proof techniques are easier to get or work with for certain problems. And that's what we are trying to tell you. Now this was what we have done till the last week. So in this particular video, we will look at the case when the statement that we have asked to prove is actually false. For example, we can get some problem like prove or disprove A implies B. And let's assume that this statement is actually false. That means A does not imply B. So if A does not imply B, or if A implies B is not true, then what do you do? Now the thing to note here is that a statement is not true if for some setting of variables to true or false, the statement is false. Meaning, can I somehow put the variables to true and false and get some wrong false statements? So in something like the true implies false kind of statement. So in other words, we have to prove that the not of A implies B is true for some instance. Where there is an instance for which we can see that A implies B is not true. Sorry, A implies B is not true, or in other words, not of A implies B is true. Now, so to prove that not of A implies B is true for some instance, how do you go about it? So usually the problems are of the form for all x or there exists x, something happens. So say the problem is of the form for all x prove that ax implies bx. So the negation of this one, as we have seen, is that it is there exists x and ax implies bx opposite, or in other words, ax does not imply bx. Now what do we mean by ax does not imply bx? Recall that A implies B is same as B or not A. So that means the negation of ax implies bx, or that means ax does not imply bx, is same as not of bx or not of ax. So not of the bx or not of ax, which is by De Morgan's law, there exists x as a not of bx and ax. So in other words, you have to produce an x such that bx does not hold but ax holds. Right? So this is what we have to prove. So to disprove, in other words, to disprove a statement of the form A implies B, which is of the form there exists x, ax implies bx, one has to produce an x such that bx does not hold and ax holds. So to prove the original statement is not true, we have to find an x such that this statement is true. And this is what we call proof by counter example. So this is one of the few cases where an example can give you a proof. So we'll see a couple of examples, problems in this case. So look at the first problem. So this is a problem that we started our videos in the first video only. So this problem says that prove or disprove for all positive integer n square minus n plus 41 is prime. Now, how to disprove it? The way to disprove it is to produce an n such that n square minus n plus 41 is not a prime. Okay? So if the statement is not true, we have to find an n such that this number is not a prime. Now, producing such an n is not necessarily the easiest job here. For example, one can try to prove that, one can check that if I put n equals to 1 or 2 or 3 or 4 or 5 or so on, it will always turn out to be a prime. The lowest n for which this number is not a prime is unfortunately as high as 41. So only when we put 41, n equals to 41, we realize that this number is not prime. Thus, we disprove the statement by demonstrating a counter example here, which is n equals to 41. Finding this counter examples are not at all easy, and sometimes, depending on the problem, can take a lot of hard work. In fact, there are problems for which the counter examples have been found after centuries of hard work. So one such example is, say, prove or disprove for all positive integers n, 2 power n plus 1 is a prime. Now these are what are known as the Fermat primes. Fermat, after the very famous French mathematician Fermat. He was there over a century ago, and he had posed this problem. Unfortunately, for n equals to 1, it is not that hard to calculate and see that, oh, it comes to 3. It's a prime. For n equals to 1, it is 5, which is a prime. N equals to 2, this number again, the 2 power n plus 1 becomes 70, which is also a prime. N equals to 3, it's again a prime. N equals to 4. Now already you can see that the things are becoming very complicated here. It's 2 power n, which is, in other words, 2 power 4 plus 1, which turns out to be 65537 is a prime. Now what about n equals to 5? And what it turns out is that n equals to 5 is this horrendously big number 429,67297, which is actually not a prime because it is a product of these two numbers. As you can see or imagine, first of all, proving that this number is not a prime is not at all an easy job because the prime factorization is quite complicated. So, to prove or disprove this statement, whether 2 power n plus 1 is a prime, is not necessarily always easy. But sometimes this is the only way of proving or disproving some statement. Thus, what we can say is that to disprove a statement, one can do so by giving an instance where the statement fails. We can prove, we call this thing proof by counterexample. And founding a counterexample can be very hard and require both ingenuity and sometimes very high computational power. So this demonstrates one more example of proof technique, namely counterexample, a very useful proof technique for proving or disproving a statement. Note that proving a statement is not necessarily the easiest job, and neither is disproving a statement. In both of the cases, we need proper proof techniques. Till now, we have looked at the proof by construction or constructive proof, proof by contradiction, contra-positive, and proof by counterexample. In the next week, we will continue our study of proof techniques by looking at proof by induction, an extremely powerful proof technique that we will be looking at. Thank you.